Carolyn Kierans. Thanks, Drew. I'm a research scientist at NASA Goddard, and I'm happy to be moderating today's session. So this is our first installment of the Frontier Seminar Series in 2026, so welcome. And as a reminder, this seminar series is organized by the AAS Head Executive Committee, and we're focused on providing opportunities for early career scientists to present on their research to the head community in a virtual forum. So we do this 3 presentations for 1 hour slot every 2 months. And if you're interested in nominating yourself or other early career researchers you know, and or seeing past presentations, you can check out the website. So I'm going to put it in the slot or the chat. And actually, Drew, can you put it in the chat briefly? The AAS Head website for the Frontier Seminar Series specifically. So today we have 3 presentations, 15 minutes each. Drew Valia and I are co-organizing this series, so we're going to be moderating today's questions. If you have questions after the presentation, we're just going to ask you to either raise your hand and you'll be able to unmute yourself and or post a question in the chat for us to read out loud. So today we're going to start off with Vishal Tiwari. He's going to be speaking about radiation magnetohydrodynamic simulations of accretion flows around massive black hole binaries. So Vishal is a PhD candidate in physics at Georgia Institute of Technology, working with Prof. Tamara Bogdanovic. I'm going to screw that one up. His primary research focuses on utilizing radiation magnetohydrodynamic simulations to study accretion flows around massive black hole binaries. And before his PhD studies, he earned a master's in science and physics from the University of Massachusetts, Dartmouth, focusing on exploding white dwarfs with Robert Fisher. And he also has a BTech and MS in computer science and engineering from IIT Hyderabad in India. So take it away, Vishal. Thank you.
All right. Okay. Thank you for the introduction. So today I'll be talking about radiation magnetohydrodynamics. I know it's a mouthful, so I'll just keep it like RMHD, simulations of accretion flows around massive black hole binaries. And so this work has been done with the former postdoc here, Edwin Chan, with my advisor, Tamara Bogdanovic at Georgia Tech, and collaborators, Yanfei Jiang, who's at CCA, and Shane Davis, who's at University of Virginia. All right, so let's get started. So what are massive black hole binaries and how do they form? So these are like gravitationally bound objects, which typically mass in the range from like 10 to the 6 to 10 to the 10 solar masses. So they're like really massive objects, and they form in the aftermath of galaxy mergers. So when these individual massive black holes, which are the center of these galaxies, go from like thousands of parsec separations after galaxy mergers due to dynamical friction and dynamical friction because of the background stars and gas, they go to like subparsec scales where gravitational wave emission becomes dominant, and they merge to form like a single black hole. Now, if these systems are in gaseous environments, they can emit light, electromagnetic radiation, and multi-messenger detection of these EM emission with gravitational waves can be used to test theories of gravity in the strong field regime, and they can also be used in to put better constraints on the expansion rate of the universe. So what does this gaseous environment look like? So the binary is surrounded by this accretion disk, which is called a circumbinary disk. It's similar to like a single black hole accreting gas, but because now we have a binary, these binary torques carve a low density cavity in the center of this disk, which is roughly the size of twice the binary separation. There are streams that emanate from the inner edge of the circumbinary disk, and they feed the individual mini disk that form around the individual black holes, as you can see in this cartoon picture. Now we do like RMHD simulations of this system, and because these computations are so expensive, what we do is like we divide the problem into 2 parts. So first part is like we simulate the circumbinary disk where we exercise the central region so that we don't simulate the mini disks. And so that part is done by me. Edwin, who's the postdoc, he does the mini disk simulation where he feeds stream into the domain, which forms the mini disk, and he does the simulation for a single mini disk. And I'll be talking about both of them today. So here are these are the parameter of the system that we simulate. So we look at an equal mass binary of total mass 2 into 10 to the 7 solar masses. They orbit in a circular orbit and they're separated by 100 gravitational radii. At this separation, the orbit takes like 7 days and they'll be emitting gravitational waves and they'll merge over a time frame of 24 years. So these systems will be precursors to LISA, the mission which will be launched in like 10 years time frame. Okay. So before going on to the results, so like let's ask the question like why do we need simulations? It's basically because they look really cool, but also they help us calculate the EM signatures of these systems. So there have been a large variety of these simulations ranging from just electrovacuum, where people evolve the magnetic field in dynamical spacetime to understand how jets are launched and how they interact, to 2D hydro simulations, where people can run these simulations for like very long time, ranging from thousands and thousands of binary orbits to understand the dynamics of gas and of the circumbinary disk and the mini disks, to even full GR MHD simulations. But one of the limitations of these simulations are they don't self-consistently model the thermodynamics, which means that they usually ignore radiation in these simulations. So in our work, we have included radiation by solving the full radiative transport equation and couple that to the equations of magnetohydrodynamics. Okay, so let's look at the first part where we simulate the circumbinary disk. We exercise the mini disk. As you can see, there's a cutout here. What you're looking at is the surface density movie of two sets of simulations. One is a simulation which has radiation included with adiabatic equation of state for the gas, and the other is without radiation with an isothermal equation of state. In both the simulations, you can see that the binary torque carves out a cavity at the center, and there are streams which emanate from the inner edge and go towards the individual black holes. And there's a lump that forms at the inner edge of the circumbinary disk in the MHD case. But when we include radiation, you can see that the whole disk kind of becomes filamentary. And the overdensity that forms at the inner edge really doesn't stand out at the background of uh, the whole filamentary structure. Uh, it becomes weaker. The streams also become weaker as compared to the MHD simulation. Next, we can look at the vertical structure of these two simulations here. What you're seeing is azimuthally averaged density of the MHD compared with RMHD. You can see that when we include radiation, the whole disk becomes much more denser in the midplane as compared to the MHD disk, and it's way more thinner. This is because radiation can easily escape the disk and it reduces the pressure support for the disk against gravity. On this side of the slide, you can see what does the height of the disk vary with the radius. And how this is calculated is how does the density drop from the midplane. So you can say like, okay, if the density drops by 1 over 10 or 1 over E for these two simulations. And why this is important, because if you have been following the literature recently about what happens to the binary if they're embedded in a disk, if you have very thick disks, the binary can expand. And if you have thin disks, the binary would shrink. But the H over R is like a free parameter in those simulations. But when you include radiation, the H over R is self-consistently modeled. So in our case, when we have sub-Eddington circumbinary disk, around like 2 into 10 to the 7 solar mass binary, we find like the H over R is of the order of 2 to the 4 into 10 to the minus 2, which means like if we have like hydro simulations, this part of the parameter space would lead to the binary to be uh, to coalesce rather than expand out. But this is assuming that the alpha disk simulations are correct. Uh, Now, because we have radiation inbuilt into our simulations, we can calculate what is the luminosity that comes out of our disks. So here, what you're looking at is like a top-down view of. So we put like these concentric hemispheres on top of a circumbinary disk at different radii, ranging from 150 Rg to 200 Rg and 300 Rg. And we integrate the radial radiation flux over these surfaces and calculate these light curves. And what we find is the light curves corresponds to the binary orbit, like half the binary orbit, which happens because you have the inner cavity, which becomes lopsided and eccentric. And every time the binary comes closer to the inner edge, it accretes gas from that eccentric cavity. And there's also periodicity corresponding to the overdensity that forms and which is orbiting the inner edge at like 5 binary orbits. Next, we can look at what does the radiation temperature look like and what kind of a thermal spectra it produces. So we have like realistic opacity prescriptions in our simulations. And what you're seeing here on the right is the azimuthally averaged radiation temperature. And the lines that you see are just different definitions of photospheres. So the black one is the Roslin photosphere, and the blue or the cyan one is the effective photosphere. And we read off what the temperature of the radiation is at those locations. And what we find is the temperature is like roughly around 2 into 10 to the 4 Kelvin, which corresponds to an emission which is peaking in around optical UV part of the thermal spectrum. If we compare this, the output that we get from the radiation hydrodynamic simulations as compared to like an alpha disk, where we cut off the inner boundary at like 200 Rg, which corresponds to the cavity, we see that it underestimates the true thermal spectra. And if we assume, like we use the gas temperature and Thomson opacity to calculate the effective temperature, we see that using that method like overestimates uh, the thermal spectra, like by a lot. This shows like why we should include radiation into our simulations and why they're so important to do. Okay, so I've been talking about the circumbinary disk. Now I'll be shifting gears and talk about the mini disk, which forms around a single black hole. So these simulations are done by Edwin, and what you can see here is what he does is he goes into the co-rotating frame of one of the mini disk and he feeds gas through stream here, and it self-intersects with itself and forms these mini disks. You're seeing like one simulation with radiation and one without radiation, and both the simulations you see there is this ring, over dense ring that forms at around 5 Rg in both simulations, and when you include radiation, the disk becomes much more denser and thinner as compared to the one without radiation. This slice is showing colloidal slices of density, and you can see that there's a two-component structure. One is this mini disk, which is like at the midplane, and the other is like this extended low-density envelope around this, which is feeding this overdense ring. The lines are showing the photosphere, and you can clearly see that the structure is very non-axisymmetric. If you look at the region where the stream is impacting the mini disk, you have this extended photosphere, like which is much more, uh, which has a much more height as compared to the other parts of the mini disk. Uh, this is showing the average photo. So this part is showing the average photosphere of the mini disk, and you can see that it's kind of bent and wavy. So it's not like flat as you might expect, and this might lead to like very interesting radiation signatures that I'll talk about later. On this side, what you're looking at is the color temperature, which is basically the radiation temperature at the photosphere. And you can see the temperature around 10 to the 5 Kelvin, which means that the thermal spectra would be emitting at the far UV part of the spectrum. Now, just looking at what is the effect of this non-axisymmetric photosphere. So what happens, like radiation which is coming from the inner edge is kind of blocked by this uneven shaped photosphere, which leads to this weird or non-axisymmetric emission from the mini disk. Uh, and if we superimpose this non-axisymmetric emission from the mini disks, and you look at what is the angle at you look at the mini disk, and you associate that with the binary, you see that this non-axisymmetric thing will be associated with the binary period. Uh, so we have some like binary period associated with this non-axisymmetric disks. Uh, I think I'm almost out of time, so I'll just leave the conclusion here. These are the links to the paper, and I'm happy to take any questions.
Thanks, Vishal, and thanks for staying on time. Appreciate it. We'll open up the room to some questions, so please raise your hand or put a question in the chat. There is a question in the chat from Michael. Michael, do you want to try unmuting first and see if we can do it? If not, I can read
Sure.
your question. Yes.
Can you hear me?
Yes,
Okay,
go ahead.
Vishal, that was an excellent presentation. Thank you.
Thank
As you
you.
might imagine, I have questions. I've asked you questions before, and I'll ask you more again. But in this case, I want to ask one question. Suppose you included simply a cooling function instead of solving the radiative transfer equation. Are there features that you would miss and features that you would capture compared to the full treatment that you?
Yeah, that is a good question. That I don't have an answer to that, but I have been thinking about like doing these beta disk simulations, where you estimate like how quickly the disk cools as compared to the Keplerian time of the gas at a particular orbit. And if we include that, how does that look like as compared to the RMHD simulations? So there have been like beta disk simulations by a student from Dong Lai. I think he's at Caltech now. So he found like very interesting structures as compared to like just isothermal, but it will be very interesting to do that for sure.
Great, thank you. We can talk further at another time. Thanks very much.
Any other questions in the room? I'll ask one as a complete non-expert in any way. Can you speak to some of the limitations and the challenges of dividing the simulation up, right? You have the mini disk simulation and then you have the circumbinary disk. What are the limitations of that?
Yeah, so one of the problems that you might have is what is the effect of like radiation from the mini disk on the circumbinary disk? So it can like just heat up the inner edge, make it more like puffier, and the disk structure might change. But these simulations are like sub-Eddington and they're equal mass case. So there have been some studies where they have found uh, so that's like the radiation part. But
Mm-hmm.
just from like hydrodynamical part, like people have found like there's like an accretion horizon, which is located at like 100 Rg, where there's like no gas that comes out of the like from the mini disk to the circumbinary disk. So we are kind of safe there, but
Okay.
the problem might creep up more when we are doing like super Eddington simulations where there might be like a lot of interaction between the mini disk and the circumbinary disk, and they're like mass ratios, they're like 0.1 or different mass ratios. So yeah, there's like a limitation that we want. That's why
Okay.
we want to do like the whole thing. That's
Yeah. Okay. Very interesting. Thank you. So I do see another hand. Paulo, thanks for raising it. However, we got to move on in the interest of time because we have two other presentations to get through. So please just get a message out to Vishal either separately or in the chat. So
All right, thanks.
thanks. Okay, so moving on. Next, we have Paarmita Pandey. She's going to be speaking to us about star-forming regions as forgers of the galactic cosmic rays. So Paramita is a fourth-year PhD candidate in the Department of Astronomy at the Ohio State University, where she works with advisors Laura Lopez and Chris Kokonek. Her research spans astroparticle physics and time domain astronomy with a focus on cosmic ray acceleration and transport in star-forming regions using Fermi. Paramita is also active in community building, and she serves on the leadership committee for the Supernova Foundation, a global mentoring program supporting women and gender minorities in physics.
Hi, thank you so much for the introduction. I'll just take a moment to share my screen. All
Perfect.
right.
We see that. Go ahead.
I hope you're not seeing my presenter view right now.
No, it looks great.
Okay. Hi, everyone. First of all, thank you so much for the opportunity to present my work here. I'm so excited to be talking about star-forming regions as forges of galactic cosmic rays. I'm Paarmita Pandey, and I work with Professor Laura Lopez and Chris Kochanek at The Ohio State University. So the main characters of my research are cosmic rays. They are a fundamental component of the galaxy because of the profound influence they have on galactic thermodynamics, chemical composition, and large-scale evolution. So cosmic ray feedback is now gaining increased attention and being incorporated in galaxy formation simulations. And so it's a really exciting time to be working in this field. But in order to model cosmic ray feedback accurately, we need to constrain their origin and how they propagate in the galaxy. So the canonical picture is that supernova remnants are the dominant sources of galactic cosmic rays. But now there is growing observational evidence towards young massive star-forming regions that can act as potential contributors. And that is the space my work lives in. So in today's talk, I'll specifically focus on two types of star-forming regions. First is young massive star clusters, or YMCs. These are systems less than 3 megayears old, where no supernova have occurred, and they are dominated by powerful stellar winds from massive OB type stars. And the second, a more exotic and less studied class that I will talk about, are explosive dispersal outflows, or EDOs. Both of my studies are pilot works. We are building the observational foundation for understanding these environments as cosmic ray accelerator. So beginning the first part of my talk on young massive star clusters, how does acceleration work in these environments? So in young massive star clusters, the stellar winds from massive stars collide and drive strong shocks. There is a forward shock, which is moving in the ambient ISM, and as a consequence, there is a reverse shock. And particles can be accelerated at both the forward shock or the reverse shock through diffusive shock acceleration. And once accelerated, the cosmic ray protons will interact with the ambient gas to produce pions, and the neutral pions decay into gamma rays. So this means that gamma ray emission is a direct tracer of hadronic cosmic ray interactions. And that's what we exploit with the Fermi Gamma Ray Telescope. However, if you have seen the Fermi All-Sky map, you would know that the galactic plane is crowded with gamma rays from pulsars, supernova remnants, and other galactic sources. So in order to constrain the physics, we decided to use the star-forming region RCW38 as our laboratory. Why this is the perfect source? So RCW38 is a young star cluster, which is only 500,000 years old. So no supernovae have occurred in this region. It is present a degree south of the galactic plane, so it is not in a very crowded region near the galactic plane. And it has dozens of confirmed OB stars, which makes it a great laboratory to constrain cosmic ray physics. So the image here on the left is the three-color image of the star cluster with Spitzer 3.6 micron data, which is tracing the hot dust in the star-forming region. We have the Chandra X-ray in the green dots, which are tracing the massive stars. And finally, we have the diffuse Fermi emission in blue. And so we do detect the star-forming region in gamma rays. Here's a TS map above 2 GeV, which is when Fermi's spatial resolution is 6 arcminutes, so we are able to localize the gamma ray emission. And the green contours show here the infrared extent of the star cluster from the previous Spitzer image that I showed. And the gamma ray emission is spatially coincident with the cluster. So we get a total 22 sigma detection across the Fermi band of this source. Next, from the Fermi data, we model the spectrum of the source, which is a beautiful power law with a photon index of 2.34, and it is consistent with hadronic emission from accelerated protons. And integrating the spectrum, we can get the total gamma ray luminosity. Once we have the total gamma ray luminosity in hand, we can compare it with the stellar wind luminosity. So I want to talk here about, as an observer, what are the quantities I can constrain with Fermi observations? And these are the gamma ray luminosity, the stellar wind luminosity, which I used from previous observations, and the effective number density of nucleons encountered by the cosmic rays in the region. And so now, once I have these observables in hand, we can constrain the cosmic ray acceleration efficiency, which is what fraction of the stellar wind energy goes into cosmic ray acceleration. This value is usually 10% for supernovae. Secondly, we can constrain the diffusion coefficient, which is a measure of how fast cosmic rays are escaping the system. And mathematically, this is how it is represented. So I will start by showing this equation, which is the main crux of the problem. The maximum observed gamma ray luminosity has to be some fraction of the stellar wind luminosity. And the equation here is showing the calorimetric limit, which means that all the cosmic rays that were accelerated hit the dense gas, produce pions that give us the gamma ray observations. However, in reality, most of the cosmic rays diffuse, and there's always a competition between the diffusion time of the cosmic rays and the pion time, which means when they are hitting the dense gas. So in our analysis, what we found is that eta cosmic ray and diffusion coefficient are degenerate parameters, which means they cannot be constrained independently, and we have to assume a value of 1 to constrain the other. So mathematically, this is how it's represented. Let me first start with eta cosmic ray. So if we assume a value of diffusion coefficient, that is the canonical value used for the interstellar medium, we find that eta cosmic ray is 0.4, or 40% of the stellar wind energy goes into cosmic ray acceleration. Alternatively, we can fix or decide a value for eta cosmic ray and constrain D. So we use the canonical value used for supernova remnants, which is 0.1 or 10%, and we find that the diffusion coefficient is at least an order of magnitude smaller than what we see in the ISM. And so what this means is that cosmic rays are being trapped in the region for a longer period of time. Both these scenarios are physically interesting. So either the star-forming region is extremely efficient at accelerating cosmic rays, or the cosmic rays are being trapped inside the cluster and are confined longer than they are in the ISM. I want to quickly mention that we also performed a diffuse X-ray analysis of RCW38 using Chandra data. So the image on the left shows the diffuse X-rays with point sources removed, and this is tracing the shock-heated gas. And using spectral fitting, we found a temperature of 4.5 keV, which corresponds to millions of kelvins of gas. This is very hot gas. And this allows us to also calculate the thermal pressure of the region, which we will later use to compare against the cosmic ray pressure. And again, what we find is that the cosmic ray pressure is 4 orders of magnitude lower than the thermal pressure. So this implies that cosmic rays might not be as dynamically important in these young star-forming regions. On galactic scales, we know that cosmic rays play an important role, and the pressure from cosmic rays can launch galactic winds. However, when it comes to these microscopic young systems in the galaxy, we find that thermal pressure is still more dominant. So I will summarize my part 1 of the talk. And the main takeaway result is that we find eta cosmic ray and D cannot be independently constrained. What we can constrain is their ratio. So either the cosmic ray acceleration is very high or the diffusion coefficient is suppressed relative to the interstellar medium. And the cosmic ray pressure in the region is subdominant to the thermal pressure. This work is published in APJ for those interested. So, in part 1 of my talk, my focus was on young star forming regions where stellar winds are driving cosmic ray acceleration. But what about systems that are still undergoing star formations and they do not have OB stars? Can they accelerate cosmic rays? Which now brings us to the second part of our talk, talking about EDOs. So I'm sure most people are familiar with protostellar outflows. These are collimated bipolar jets launched by young stellar objects, like the one shown in the image here. But explosive dispersal outflows, or EDOs, are something quite different. They are more isotropic, more energetic, and much more violent. So here is an image of the Orion BNKL EDO. Talking about their properties, these explosive events result from the dynamical disruption of a young, massive stellar system, like the merger of protostars, and they release at least 10 raised to 46 erg of energy in their environments. And they consist of straight, narrow filaments, CO filaments, and they are isotropic in nature, which is quite different from what we observe in protostars, which is bipolar. And they all point back to a common origin. So they have been discovered using the ALMA telescope. The occurrence rate of EDOs in the galaxy is once every 100 years. So this is just like supernovae. And this beautiful animation here shows the EDO in Orion. This is comparison from Subaru versus JWST, and you can actually see the filaments moving in time. So here is the known sample of EDOs in the galaxy. Only 7 of them have been detected so far, and they show a variety of ages. The youngest, Orion BNKL, is just 500 years old. This explosion took place 500 years ago, and the older systems like DR21 took place at least 10,000 years ago. And the symbol size shows their range of their kinetic energies. And for 2 of them, with the red circles here, they had associated Fermi sources in the 4FGL catalog. So I investigated gamma ray emission from all these systems, and we found 3 confirmed detections of EDOs in gamma rays, with the brightest being DR21. So here is their TS map and their spectral energy distribution. Their spectra usually cuts off at 10 GeV, which is something we noticed. But here is the star of my work, the highest detected EDO DR21. This is located in the Cygnus X star-forming region, which is one of the most active star-forming region in the Milky Way, and it hosts deeply embedded massive protostars. And we detect it at greater than 40 sigma significance across the Fermi band 0.2 to 500 GeV. There are no massive stars, supernovae, or compact objects nearby. It is just coming from these embedded protostars. And so applying the same framework as part 1, we were able to constrain the calorimetric cosmic ray acceleration efficiency to be no more than 15% of the outflow's kinetic energy. So to summarize part 2, across the EDO sample, no more than 18% of the outflow kinetic energy goes into cosmic ray acceleration. And when we account for the event rate of the EDOs across the galaxy, we find that they contribute to at least 1% of the galactic cosmic ray budget that has been traditionally attributed to supernovae. And it's a lower limit because there are possibly more EDOs in the galaxy that have just not been discovered yet. And this work is also was recently accepted in ABJ for publication if anyone is interested. So here is the big picture plot that puts everything together. The phase space of young massive star-forming regions as cosmic ray accelerators. We have the gamma ray luminosity on the y-axis and the total mechanical energy of the system on the x-axis. The young massive star clusters are shown in black. Protostellar outflows, only 2 of them have been detected with Fermi so far. They are in blue, and the EDOs are in red. And the dotted lines here show the cosmic ray acceleration efficiency. And I want to be precise about what these efficiency values represent. So for each source, eta cosmic ray is derived assuming a standard diffusion coefficient. But as I showed for RCW38, eta and d are degenerate parameters. So what we are really constraining is their ratio. So this plot is best read as showing the ratio eta over d normalized to a standard diffusion coefficient. And a higher position on this plot means either more efficient cosmic ray acceleration or cosmic rays being trapped, or both. So all these sources roughly follow a same trend. They span many orders of magnitude in mechanical energy, and most fall between less than 10% of calorimetric efficiency. So this tells us that there is something universal about particle acceleration in star-forming environments. So the headline result is that before the first supernova ever goes off, star formation and massive stars are already loading the galaxy with cosmic rays. And from stellar events in young massive clusters alone, we are looking at somewhere between 1 to 5% of the galactic cosmic ray budget, and EDOs add another 1%. And so these are pilot studies, but they point towards star-forming regions as genuinely important and previously underappreciated component of the galactic cosmic ray system. Thank you.
Thank you so much, Paarmita. Very interesting talk. I'll open the room for any questions. Please raise your hand or type into the chat. So while we're waiting, so these EDOs, these are really interesting. I had never heard of these before. Can I ask, is there expected to be kind of a transient signature when these actually go off? Because you're only observing these, 500,000 years after they've gone.
Right. I believe so, given that they at least like have 10 raised to 46 to 10 raised to 49 erg energy.
Yeah.
I believe so. And it would be interesting. However, like they're very small, roughly 1 to 2 parsecond size. So, which is why we need ALMA's spatial resolution to detect them. So I feel like detecting them is quite hard, and we need like very good spatial resolution telescopes.
Yeah, and quite a bit less luminosity than GRBs, so not
Yeah.
super bright in the high energy transient regime. Okay, interesting. Thank you. Any other quick questions from the room? Okay, thanks again, Paarmita. That's great. So we're going to go for our last talk for today. So Xiaojie Wang is going to talk to us about the impact of wide field ground-based gamma ray observations on multi-messenger astronomy. So Dr. Xiaojie Wang is an assistant professor at physics at Missouri University of Science and Technology. And before joining Missouri S&T, she was a research assistant professor and postdoctoral researcher at Michigan Technological University. Her research focuses on very high energy and ultra high energy gamma ray astrophysics, with an emphasis on identifying cosmic particle accelerators in our galaxy. She works on ground-based observatories, including Hawk and LASSO, and is also involved in the development of SWIGO. Her research spans pulsar wind nebula, supernova remnants, gamma ray binaries, TeV, halos, and other extreme high energy sources. And she has led the discovery and analysis of ultra high energy gamma ray emission from the microquasar V4641 Sagittarii in 2024. So Xiaojie, go ahead.
Yeah, thank Karen, for your nice introduction. Am I open my voice?
Slides look good. Yeah,
Can you
go ahead.
hear me?
Yes.
Thank you. Thanks for the nice introduction again, and I'm very happy and honored to be here to talk about my research.
Xiaojie, I'm going to interrupt. Xiaojie, can you hear me?
Discoveries, and also talking a little bit more astronomy here. Yes, I can hear you.
Yeah, sorry,
can you hear me?
Yeah, your signal's not super strong. I might actually recommend you turn off your video just so we have the audio stronger.
Sure, that also works. So let me hang on.
Sorry about that, but
yeah,
want to
no
make sure
worries.
you come through loud and clear.
Yeah, sorry about the internet connection issue. So all right, so continue. As we all know that for a long time, our astronomy is totally or almost entirely rely on photons. But after decades of development, now we have entered an era of multi-messenger. We have different messengers from the universe to carry different pieces of information from it. So all these four main messengers are cosmic rays, neutrinos, photons, and gravitational waves. If we combine all this information from different pieces of that, we will have a complete picture of the extreme astrophysical environments. So among these, gamma rays is playing a crucial role, but detect gamma ray at a very high energy end is non-trivial. So from the right lower corner of the plot, you could see that we have different instruments to cover different aspects of the mass. For gamma rays specifically, we have space-based satellite detectors like Fermi and Swift. And for the ground-based instrument, we have Hawk and Astronomy as another generation with CAO and other particle. So why gamma rays are interesting and important during this procedure? So if we take a step back from our whole universe to this local extreme environment, which is maybe in the binary system or in a star-forming region, like Paarmita have mentioned a little bit, and the supernova remnants and even galactic active galactic nucleus. Gamma rays, all these objects, we could treat them as natural particle accelerators. So for gamma rays, they will provide the direct probe of this particle or cosmic ray acceleration site because they are produced in the interaction of the cosmic rays and their surrounding environment. While neutrinos, on the other hand, could be a smoking gun of the hadronic process. And gravitational waves can help us identify an astrophysical environment where the cosmic ray acceleration is possible, such as binary mergers, especially for neutron-neutron star mergers. So if we combine this information together, we will know that we could solve or we could address several key different questions in the astroparticle physics, like was suggested in the decadal survey on the Astronomy and Astrophysics 2020. So at the right-hand side is a plot that I grabbed from the Astro 2020 report. We could see that different combinations will tackle on different scientific topics here. So if we combine gamma ray and neutrinos, we could We could touch on the causations of the AGN jets, and we could also understand more about the Milky Way TV gamma ray sources. And if we add in another messenger, which is cosmic ray, in, we could understand more about the origin of the galactic cosmic rays, which is a centuries mystery since cosmic ray has been discovered in 1912. And we also understand more about the ultra high energy cosmic rays origin. But if we add another matter in, which is gravitational waves, we will have better understanding of the relativistic jets and particle radiation through the whole universe. We could have a deeper understanding of the dark matter. We have some more interesting transit events. But one challenge for these multi-messenger events that most of them are transient events, as we have said. So they are unpredictable. These examples including some gamma ray burst and gravitational wave events or neutrino alerts inside our field. So we need an instrument that could cover a large portion of the sky all the time to do the sky monitoring. This is where this wide field view gamma ray observatories become extremely valuable. So if we example, one of these main instruments was HAWK, which is short for High Altitude Water Turn-Off Observatory. For people who are not familiar with it, it is looking a slope of a volcano mountains and at the high altitude of 4,100 meters high in Mexico. It was consist of the 300 main water tanks, which is marked in the red zone. So if you took a look at the left part for these main tanks, we have the scale almost like the T-Rex. And we have 4 PMTs anchored at the bottom of water tanks, which is fulfilled with a purifier. We use that as a medium to detect the Cherenkov light emitted by the relativistic secondary charge particle produced by these original or primary particles. How we could see that it a large field of view, its instantaneous field of view is 2 steradians. And if a high duty circle can work always as some power of things like that on. So we could do the out-sky monitoring without recounting if an interesting events came in by the real-time alert stuff. So continuous, we could do the real-time analysis and real-time alert decimations. We could even go to this archival data and source catalog to search more deeply into our data to trace back to the events. So to give you a more vivid impression about how our field of view is looking like, so you could check the animation at the right upper corner with that blue zone, blue to red zone will be our field of view and how it changes in 24 hours. It shows that we can cover most of the northern sky in 24 hours. So that all these characteristics mentioned here is about how are suitable for the transient catches. But HAWK is not just a gamma ray observatory. It was designed as a multiple purpose instruments that could contribute to a broad range of astrophysics and fundamental physics research. So inside our collaborations, our science working group are structured to target at different aspects of the energy phenomena. I have been leading the galactic binary star-forming region, other unidentified sources. But beyond the domain, we also have the extragalactic working group, which is could focus on more of these gamma ray burst. Will involve more multi-messenger stuff. even with other facilities like IceCube and LIGO to connect neutrinos, gravitational waves, and gamma rays together. And beyond that, we also have the cosmic ray physics and also study on the particle physics like dark matters and black. Move to some true scientific topics. Here we show a multi-messenger view of the Milky Way. So we have 3 plots here, 3 maps here. For the first, for the top panel, we have the view how it was we call it almost 3,000 days of data, and in the middle panel that was from Fermi, it was the high energy gamma ray sky. At the bottom panel, it is the neutrino signals through by comparing these similarities and discrepancies and combine gamma ray data and neutrino observations, we can search for some potential cosmic ray accelerators in our galaxy. Speaking back to how gamma rays could impact the multi-messenger studies. So from my perspective, I was divided into 3 cases. One is for population study, and the other is we could do some follow-up studies for these transient signals. And the last one will be discovery studies, which is instead of follow-up other studies, we could produce some new discoveries to the whole community. Let's take an example. So here, one of our recent study is using raw data from both HAWC and the IceCube, which is we did don't likelihood analysis to search the multi-messenger signals from the potential galactic cosmic ray accelerators. This work has jointly analyzed 22 sources that assume gamma rays are totally produced from the accelerated protons. In software, we call multi-mission maximum likelihood framework, which is we also call it 3ML. And I listed as the left hand side to show this. While there is no significant signal emissions were detected through this work, the beauty of it is that we are at the significance of real data analysis using the same software framework instead of just using some flex point or upper limit as most joint analysis do. And it can be clearly extended to other wavelengths and messengers. So 3ML already have several plugins for multiple instruments. Well, I listed them in the left-hand side. Maybe so the only missing part will be the gravitational wave information. So maybe we could include it in to complete the big picture. So another example involves the studies of the pivotron candidates. Pivotron means that the sources could accelerate particles to PeV energy range. So why PeV energy range is so important? Because that is we have in our galactic cosmic ray energy spectrum, we have a structure called the near region, which is we have changes of the indices of the cosmic rays, and so people are still debating what is the origin of the cosmic ray at that specific region. Why the near region is so important and why the pivotron studies are so important. So back to our work here. This is a work involvement of multi-wavelength analysis of a source called LASSO J2108. So here we're using 2,500 days worth data from HAWC, and we have about 7 segmentation of this source. And but using Veritas data and XM data, we can only yield the upper limit so far. There is no clear accelerators in the vicinity of this pivotron candidate. show that both leptonic and hydrogen the gamma ray emissions so far. So if we could have a deeper multivalence analysis, or if we could have a multimeter involved in, let's say, neutrino, it will be better to understanding this interesting cells. And our collaborators forgot to mention that from Michigan, from Maryland, from Goddard, and Columbia University. So these are some examples of the population study. As we have mentioned that we could also do some follow-up study for these transient signals. So in this slide, I listed the existing multi-messenger alert system, which could enable a rapid follow-up of these transient events such as gravitational wave and GRBs and neutrinos as shown in the left plots. And I also listed other tools that could available to do this. So I have mentioned that besides this follow-up, we could also do some discover new sources for the community. One of the would be my latest project, which is involved in W4641. It is microquasar, which have one of the fastest subliminal jets in our Milky Way galaxy. So if you look at take a look at the plot here with a partial sky map, I show at the upper panel. It is this microquasar is below our galactic plane and edge of the Hawk field of view, and it was first detected in the gamma ray by Hawk in 2024 with a significance of 8 sigma. And this also has also interestingly X-ray outburst with about a 2-year scale. So energy spectrum of this analysis of this source has shown that these cells have a very high, very hard spectrum, which is could last to over 200, which is could also to 500 TeV by the confirmed by the last collaboration. This could prove that microquasar could be so significantly contribute to the galactic cosmic ray energy spectrum, especially at the PeV, and it has also triggered a lot of interest and discussions in the community. It also triggered many follow-up studies. So here is one example that we know that science thrived on collaborations. We all sit on the giant's shoulders to have a better understanding of our science topic. So after this source was detected, we have started information to the whole collaboration, the whole community through MOU. And in this slide will be the follow-up collaborations through the whole electromagnetic energy spectrum. So we also have some multi-messenger follow-ups. So that is
sorry, Xiaojie. Yeah, we're approached the end of the hour. So can you just quickly wrap up with another sentence, and then we'll open for questions.
Sure. Sorry for this. So this showed us how gamma rays could contribute to this fascinating multi-messenger, and we would like to continue this success in the southern hemisphere, which is amazing half of the sky. So SWGO will be the one of these great instruments, also be a complementary of the CTAO observation, and to continue the success in the northern sky with a better sensitivity curve. That is all. Thanks. I'm happy to.
Okay, thanks a lot, Xiaojie.
I'm happy to take questions from now on. I'm sorry about the over.
It's okay. It's okay. No worries. Understand how it is. So I'd like to open the room for questions for anyone. So maybe I'll start. Since I'm not as familiar with the ultra high energy push these days, can you speak to the main science motivation or main science goals of SWIGO or SWGO? Is it trying to go after these galactic cosmic ray sources, or is it something more?
Yes. So it is basically have the similar scientific goals as Hawk have, but we are covering a different portion of the sky. Since the current ground-based gamma ray instruments are all listed in northern hemisphere, like Hawk and LASSO, if we didn't speak ICTs. So we are still missing part of the sky that is the southern hemisphere. So through the SWGO, we could cover better of the galactic centers, which is have so many fascinating activities happening there. And we could also have more discoveries in the southern sky, like a more binary system, especially in the galactic inside our galaxy. And we could have more transits from that part, so that through SWGO, we could combine Hawk data and SWGO data and form a whole sky survey. It can be partially shown in the plot here. It is our field view of Hawk. So for this gray zone can be covered by Hawk. So hopefully this answers your question.
Yeah, definitely. Okay. Thanks a lot. So in the interest of time, and I know other people have other things to get off to on their Friday afternoons, thanks again to all three speakers. This was awesome to see such diverse research going on in the high energy community. So thank you everyone for taking the time to come and also support your early career research fellows. So thanks a lot, and we'll see everyone again in 2 months' time.